Here's another example of trigonometric substitution. Let's find the integral of the function 1 over x squared times the square root of 4x squared plus 3 dx. Now at first glance, it might not be obvious that this is a function we can use trig substitution for. We do have a square root in here, but it doesn't appear to be a sum or difference of squares. Let's go back and look at our table of substitutions that are good for trig substitution and see if we can compare. So typically, we'll use trig substitution if we see a radical in our integrand that takes the form of either a sum of squares or a difference of two squares inside the radical. So either a number squared minus x squared, or x squared minus a number squared, or x squared plus a number squared. But our radical is the square root of 4x squared plus 3. So it doesn't really appear to quite fit these terms here. But nevertheless, it seems to be most like this last one here, the square root of x plus a squared, which tells us that we should use x equals a tangent theta as our substitution. So let's try that, and let's just see if we can make that work for us. So we think we might be able to make this work with x equals a number times tangent theta. But how should we make it work? Well, here's the first thing I see. That 3 there is not a perfect square, but it actually kind of is in a way. It's actually something squared. What can you square to get 3? Well, you can square the square root of 3. So we actually do have an a squared here, and we can put our a as a coefficient in front of the tangent theta. Our a here is the square root of 3, and that should work. The other problem is that we don't just have x squared plus a squared, we have 4x squared plus a squared. But that's actually not a problem either, because something is really being squared here. It's really 2x in parentheses being squared. So if we look at it this way, we actually do have a sum of two squares in our root here. And let's just stick that coefficient of 2 in front of our x for our substitution, and we should be all set. And of course, with these problems, you can never be absolutely sure that it's going to work until you just try it. So let's try it and see what happens, and it might be that it turns out it doesn't work and we'll move on to a different solution. But it looks like this ought to work. We'll need to find our dx, but first let's just solve for x. So x is equal to root 3 over 2 tangent theta. Don't worry about that root 3 over 2. It's just a number. This is no different than the last problem we solved, where we had a coefficient of 5 in front of our trig function. This time, our number is a little bit uglier, but it's just a number. It's not a big deal. And our derivative of x, dx, is equal to, well, that coefficient goes along for the ride, so root 3 over 2, times the derivative of tangent theta, that is secant squared of theta, times d theta, of course. And finally, we'll want to make our right triangle. You can always save this till later, but I think it helps to do this step now. Often it will help you to make your substitution successfully. So this is a right triangle. Let's put our theta, our angle theta, as our lower left here, as usual. And to figure out how to label the sides of the triangle, let's just isolate that tangent of theta. So if 2x equals root 3 tangent theta, then tangent theta is just 2x over root 3. And tangent is usually opposite over adjacent, so let's label our opposite side 2x and our adjacent side root 3. And to find the last side, the hypotenuse, you can use the Pythagorean theorem. I'm not going to show you all the steps of that because you know how to do it, but if you work it out, you'll find that that last side ends up being the square root of 4x squared plus 3, which, lucky us, that's the exact square root that is appearing in our integral already. That is a sign that we have made the exact right choice of what substitution to use here, with the 2x and everything. This is a sign that we have made a good choice here for our substitution. So now we're just about ready to start doing our substitution here and plugging in all these other functions of theta in for x or for 2x. But before we do that in the entire integral, I'd like to try and tackle that radical and see if I can simplify that and work out how that's going to simplify before I try and handle all the rest of the integral. So let's just look at this root here, the square root of 4x squared plus 3. and try and simplify it. Now, of course, we know that that 4x squared is actually 2x in parentheses squared. And I know that 2x is equal to the square root of 3 tangent theta. So let's just replace that. We have the square root of root 3 tangent theta. That's being squared. And then we're adding 3. And let's have the square root of that whole thing. And we'll want to simplify this. This equals, well, the square root of, let's see, root 3 squared is 3 times tangent squared of theta plus 3. Except, oops, I'm seeing right now that I could factor a 3 out of this whole thing. So I think I'd like to do that right away. Instead of saying plus 3 there, let's say 3 times tangent squared theta plus 1. And that gives us our factoring. This is still under the square root. Now, how do we simplify this further? Now's a good time to remember our trigonometric identities. In particular, we know that tangent squared theta plus 1 is equal to secant squared theta. So we're ready to plug that in here. This is the square root of 3 secant squared theta. Now, earlier we could not distribute our square root because roots don't distribute over addition. But roots do distribute over multiplication, and our entire expression inside that radical is now a product. So now we can actually do the square root here. And the square root of 3 is just the square root of 3. And the square root of secant squared theta is secant of theta. So our entire root turns into the square root of 3 times secant theta. Now we're ready to do our full substitution into this integral. So we have, let's see, the integral of, well, that dx over there is on the right-hand side, but it's really being multiplied, which means it's really on the top here. So let's put that dx on the top. We know that dx is equal to root 3 over 2 secant squared theta d theta. And on the bottom, we have x squared. We know that x is root 3 over 2 tangent theta. And that whole thing's being squared. And then we have our square root there, the square root of 4x squared plus 3. And we already worked out that that square root is equal to root 3 secant of theta. So now we just need to figure out how to simplify this thing down and then compute the integral. Now, it looks kind of scary right now, but actually it's not too bad. It's actually just a product and quotient of a bunch of trig functions with some coefficients, and we can handle those coefficients pretty easily. So let's try and simplify it. The first thing I see here is I'm dividing by secant theta here on the bottom, and I'm also multiplying the top by secant squared theta, so let's actually cross out one of those secant thetas. And let's simplify the rest here. We have the integral of root 3 over 2 secant theta. We got rid of that square there because we divided by the secant theta on the bottom. And here's our d theta. Divided by, all right, root 3 over 2 tangent theta. That whole thing's being squared. So root 3 over 2 squared, root 3 squared is 3. Over 2 squared, that's 4. And then tangent squared theta times root 3, and that's it. Now's a good time to try and sort of pull out all of our constants, our coefficients here. So we are multiplying by root 3 over 2. We're also dividing by 3/4, but that's the same thing as multiplying by 4/3. Let's have that. We're also dividing by root 3, so let's multiply by 1 over root 3. And then we have the integral of secant theta d theta divided by tangent squared of theta. And let's just try and simplify our coefficients here. We're multiplying by root 3 on the top. We also have a root 3 on the bottom. They cancel out. That 2 and the 4 can cancel out. We're left with a 2 on the top. So our actual coefficient in front of that integral is 2/3. So let's go on a new page here so we have a little more room. We're looking at 2/3 times the integral of secant theta over tangent squared theta d theta. Now, We can use all the tactics and techniques that we have from section 7.2 here to try and handle this integral involving trig functions. We're accustomed to dealing with integrals involving secant and tangent, and typically we want to try and do some kind of a u substitution here. If the power on the secant theta is an even power, then we can probably make our u equal to tangent theta, and the du would be secant squared theta. If the power on the tangent theta is odd, then we can make our u secant theta, and our du will then be secant theta times tangent theta. But in this case, neither of those things is true. Secant has an odd power of 1, and the tangent has an even power. The power is actually negative 2 because the tangent squared is in the bottom. So rather than try and work with secant and tangent here, let's actually convert these to be in terms of sines and cosines. So we have this equals 2/3 integral of, well, secant theta is 1 over cosine theta, and we're dividing by tangent squared theta. Tangent theta is sine theta over cosine theta, but since it's being squared, we got to square both of those. So sine squared theta over cosine squared theta. Make sure when you've got a compound fraction like this that your middle division bar is bigger and very obvious, and you know what's being divided by what. And we have our d theta at the end. So we'll just simplify. This equals 2/3 integral of, well, we've got 1 over cosine theta times the reciprocal of the bottom, so that's cosine squared theta over sine squared theta times d theta. But of course, we're dividing by cosine on the bottom here, and we also have a cosine squared theta on the top, so we can cancel one of those out. And now we have 2/3 integral of cosine of theta, d theta, I'll just put the d theta on the top there, over sine squared theta. Now we can actually do a u substitution. Now that we've converted this to be in terms of sine and cosine, we're ready to go. Let's pick our u to be sine theta here. And therefore our du is, the derivative of that is cosine of theta d theta. So our integral is equal to 2/3 integral of du over u squared. Now, if you've got a power function like we do here, we want to have that power function up on the top with a negative exponent if necessary. So this is equal to 2/3 integral of u to the negative 2 du. And that's easy. At last, we are ready to do our antiderivative here. We're ready to actually find our integral. This is 2/3, well, u to the negative 1 because we had to raise the power by 1. Whenever you have a power function like this, then use the power rule in reverse like this. Raise the power by 1. We also have to divide by the new power, so divide by negative 1. And plus a constant. Clean it up a little bit here. This is negative 2/3 times 1 over u plus a constant. And now we've done the integral, let's do our back substitution here. Our u is actually equal to sine theta. So we have this equals negative 2/3 times 1 over sine theta plus a constant. But 1 over sine theta is actually a different trig function. It's actually cosecant theta. So let's just put it in that form. Negative 2/3 cosecant theta plus a constant. So we've worked out that this integral is equal to negative 2/3 cosecant theta plus c. But as always, we need to put our integral in terms of the variable that we started with. We need to have a function of x here, not a function of theta. So to work that out, as usual, we'll take a look at our right triangle that we already worked out in order to convert cosecant theta into a function of x. We want to know what cosecant theta is. Cosecant theta is the reciprocal of the sine function. If sine is opposite over hypotenuse, then cosecant is hypotenuse over opposite. So the hypotenuse of this triangle is the square root of 4x squared plus 3. And the opposite side is 2x. So this is what our cosecant theta is. Let's fill that in. This equals negative 2/3 the square root of 4x squared plus 3 over 2x plus c. And as a final step, let's just try and clean this up a little bit and simplify it. We are multiplying by 2 on the top, and we've got 2 on the bottom. Let's cancel those. And we are left with negative square root of 4x squared plus 3 over 3x plus constant. This right here is our final answer. We're all set.